A practical problem here. So a steel ball is dropped from rest from a tower 500 feet high. Answer the following questions. Take the acceleration of gravity to be 9.8 meters per square second. Okay, so the first thing we want to do is find an equation for the height of the ball after t seconds, after I've dropped it. How long will it take for the ball to hit the ground? What's the velocity of the ball as it hits the ground? And part 4, if the stone is not dropped from rest, but if the stone is actually thrown downward with an initial velocity of 6 meters per second, how long does it take to reach the ground? Okay, so let's see what we've got. So we have this tower. Let's go ahead and just draw this out. So this is the ground level, and I'm just going to make this tower like that. And they tell us that this is 500 feet high. And I'm going to go ahead and take that as ground zero. So this is the 500, right? Okay. Now, number one wanted the equation for the height of the ball after t seconds. Okay, after a certain number of seconds, the ball is going to be like right there. The height is going to be 500 minus the distance that it actually traveled. So what I'm going to do is I'm going to find an equation for the distance that it actually traveled, and then take 500 minus that. And that will give us our equation. So we will let s of t be the distance function, how long it travels. Okay, be the distance function, also called the position function. You remember we called it position before. That's the actual function that I'm looking for. I'm looking for s of t. Well, s prime of t, I know that the derivative of the position function is my velocity function. Okay, it's my velocity. And I know that if I take the derivative again, in other words, s double prime of t, that's my acceleration. That's my acceleration function. Well, what do we know? We know that the acceleration of gravity is 9.8, and it's just a constant. That's it. You're just dropping it from rest. So the only force that's acting on this is the acceleration of gravity. Therefore, our acceleration function, s double prime of t, is actually just equal to 9.8. It's a constant. Therefore, s prime of t, when I take the first antiderivative, well, that's just going to equal 9.8 t plus c1. Okay. Well, what do I know? I know that the s prime of t, which is the velocity, let's try it again. I know that s prime is the velocity. Well, I know that the velocity at time 0, which is the s prime at time 0, well, it's starting from rest. I'm just dropping it, so it's 0. So s prime of 0 is 0. So let's plug it in here. So that means that, yes, so s prime of 0 is equal to 9.8 times 0 plus c1, and I know that that equals 0. So that implies that c1 is actually equal to 0. So when I plug that in to my original equation, to my s prime, I get s prime of t equals 9.8 t. So I found an equation for the velocity at time t. It's 9.8 t. Okay. Now, I'm looking for s of t. So now I'm going to take the antiderivative of that. So now I've got s prime of t equals 9.8. Therefore, s of t is going to equal 9.8 t squared over 2 plus c2. Okay? Now, what else do I know? Now I need to find c2. Well, I know that S of t, or S of 0, in other words, the position at time 0 is 0. I take that as my 0 position, so that also equals 0. So I'm going to put that in here. So S of 0 equals 4.9 times 0 squared plus C2 is equal to 0. That implies that C2 is equal to 0. Therefore, my position function, S of t, is equal to 4.9 t squared. That means after a certain number of seconds, t seconds, I've actually traveled 4.9 times t squared feet, meters, whatever the length is. Therefore, that means that's this distance. They do it in red. After a certain number of seconds, I've traveled this distance. Therefore, my height above the ground is going to be 500 minus this distance. So my height function is going to be 500 minus 4.9 t squared. And again, this is only based on the fact that I chose this as my 0. You could have chosen this as your 0. Just a different frame of reference. Hope that makes sense. Okay, so now, how long? Number 2, let's go back to blue here. 2, how long before the ball strikes the ground? In other words, how many seconds go by before it hits the ground? How long before the ball strikes the ground? Well, let's see. So we came up with our S of t, which was going to be 4.9 t squared, right? That was our position function. Well, we're falling 500 feet, right? Our tower was this one. So we need to find out, so we're going to set S of t, which is 4.9 t squared. We're going to set it to 500. In other words, how many seconds does it take to go 500 feet? Well, when I solve this, I get t equals 10.10 seconds. Nice and simple. I have my position function. How long does it take to go the 500 feet? Okay. Number 3. Velocity as the ball hits the ground. Velocity as the ball hits the ground. Well, we said that our velocity function, which was our first antiderivative, s prime of t, we said that that equals 9.8 times t. Well, after 10.10 seconds, which is when the ball is hitting the ground, I get the velocity at 10.10 seconds equals 9.8 times 10.10 seconds. It's going to be 99 meters per second. That's it. Very, very straightforward. Okay, now let's do the last one, number 4. Okay, if our initial velocity is 6 meters per second downward, what is the velocity of the ball as it hits the ground? Okay, now let's do this again. So we'll start from the beginning. We have s double prime of t, which is our acceleration function. We know that that equals 9.8. When I take the antiderivative of that, that's going to give me my velocity function. That's what I'm interested in. So again, I have s prime of t, which is my velocity function. That's going to equal 9.8t plus c1. Okay? Standard antidifferentiation. But now it's slightly different. Now my initial velocity, in other words, my s prime of 0, which is my v of 0 is now 6. It isn't 0. So my velocity at time 0, which is 9.8 times 0 for t, plus c1 is equal to 6 meters per second. So this implies that my c1 is actually equal to 6. That goes in here. Therefore, my s prime of t function is actually equal to 9.8t plus 6. Now, when I find my s of t, I take the antiderivative again. Now I'm going to get my 9.8t squared over 2 plus 6t plus c of 2, which is equal to 4.9t squared plus 6t plus c over 2. Okay, so I have a different function now, and I also know that s of 0 is still 0, right? My 0 point is my starting point. Therefore, I've got s of 0 is equal to 4.9 times 0 squared plus 6 times 0 plus c2 equals 0, which implies that our c2 is equal to 0. Therefore, I get s of t is now equal to 4.9t squared plus 6t. That's my equation. Okay, now I need to find out how many seconds it takes now that I've thrown it with an initial velocity, which introduces this second term, which wasn't there before. Now I need to set this equal to, so s of t equals 4.9t squared plus 6t. I need to set that equal to 500. When I do that, I get t is equal to 9.51 seconds. Exactly what I expect. I threw it down with an initial velocity instead of dropping it from rest, so it's going to take less time for it to get to the ground. It took 10.1 seconds. Now it's only taking 9.51 seconds. This 9.51 is now what I actually am going to put into my velocity function, my new velocity function, which includes this extra term for the initial velocity. So now s prime of t, which is my velocity function, is equal to 9.8t plus 6. Therefore, the velocity of 9.51 equals 9.8 times 9.51 plus 6, excuse me, and I get my velocity 9.51 equals 99.2 meters per second. So not a lot faster, but certainly faster. There you go. That takes care of antiderivatives. Thank you so much for joining us here at Educator.com. We'll see you next time. Bye-bye.